really excited to have Chad Martel here tonight. He's a habitat biologist for the Hoopa Valley Tribal Fisheries, where his focus is on smaller scale restoration projects, habitat monitoring, and juvenile outmigration monitoring, both on and off the reservation. Chad obtained his undergraduate and graduate degrees from Cal Poly Humboldt, where he focused on his studies on marine and estuary fish. Tonight he's going to present the journey that juvenile Chinook salmon take from red to blue and the dangers they face along the way. With help from the Hoopa Valley Tribe, the program also has embarked on a multi-year study that aims to inform juvenile Chinook salmon survival as they complete their outmigration through the Trinity River. So please help me give a warm welcome to Chad Martel.
Thank you, Kiana. Okay, yeah, we're gonna jump right into it. So I titled this presentation "Red to Blue." We're gonna look at survival of juvenile Chinook as they are deposited in red, make their way through the ocean, and make their way to the big blue, to the ocean. These are survivorship curves. They're something that are taught in every intro to ecology course. If you're not familiar with them, I'll go through them briefly here. They're a way for us to visualize how mortality affects species as they move through life. On the y-axis, so on the up and down axis, we have the number of surviving individuals. On the y-axis is the age of the individuals. Reaching at the end would be maximum life expectancy. There's three general types of curves. There's type 1, that's the top blue line, comes straight off from the x-axis and drops down later in life. Type 1 is characterized by low mortality early in life and a majority of individuals making it to adulthood or maturity. These are termed case-selected species, and the example that we see a lot are humans and elephants in all the textbooks. Basically, these are species that put a lot of investment into a small number of offspring to ensure their best survival, right? So humans, 1 or 2 at a time, really try and put as much energy into those and make sure that they make it to maturity. Next, we have a type 2 curve, which is that middle red line where you see the bird sitting on it. This is characterized by a mortality rate that's constant throughout life. So juveniles have about the same chance of mortality as adults. The textbook example for these are birds and rodents, small mammals. And lastly, we have type 3, and this might be a little bit more familiar as we think about fish. These are R-selected species, and they're typified by early loss or a high mortality early in life that decreases as individuals age. Small fish and amphibians are again like the textbook example. So these relationships between mortality and age are fairly well established, and we see them in textbooks and papers and literature all over the place. But if we zoom in on the top left corner of that relationship, there's actually something missing here. For most species, not just type 1 and 2, or not just type 3, but 1 and 2 as well, there's typically a time of higher mortality early in life that usually starts right about fertilization. That eventually slows about at some point in the future. And this is when our survivorship curves actually start, right? So those survivorship curves ignore this high mortality early in life. From what I could find, the reasoning for this stems back to just special reasons why baby animals might die, right? It was just kind of a given that young animals die early. We really don't need to look into it. It's just kind of a fact of life. So let's start from once mortality kind of levels out, and we'll go from there. Like we see in this quote from the 1950s. But in recent decades, there's been more effort poured into these special reasons, and we're trying to find out why those juveniles die at a faster rate than we see in more mature individuals. This early mortality has been termed ontogenescence, so it'd be the opposite of senescence. Senescence is what happens when individuals get old and die, right? These are young individuals still in their ontogeny, they're still young. All right, the fact is that for most species on this planet, early life is a dangerous time. From plants and algae to invertebrates and vertebrates, early life comes with a high risk of mortality. This period, we can see that same U shape from the last slide on both of these figures. On both of these figures, the x-axis is age, and the y-axis is mortality. Any guess on what these species might be? We can see that they reach about 50 years old on this side and about 90-year-old on this side. These are actually elephants and humans, right? These are the same species that we see as examples of that type 1 curve that should have low mortality early in life. All right, so we're going to focus a little bit more on fish now. All right, so that was kind of a background on early mortality. We're going to move our focus down onto fish. Cartilaginous fish and bony fish, like salmon, are probably the poster children for ontogenescence. Is anyone familiar with the phrase, the average fish is dead? It's sort of a tongue-in-cheek way for us to describe what happens to most young fish, right? Fish exhibit a wide range of parental strategies, ranging from a white shark we see on the far right, who will give birth to 2 to 14 pups at a time after a 12-month to 22-month gestation. There's the mola mola here in the middle, the ocean sunfish. She will broadcast spawn 300 million eggs at a time into the current with very little parental care for those eggs. On the far side, we have a mouth brooder. This is a jawfish, and he'll actually hold those eggs in his mouth until they hatch, foregoing eating during that time. And of course, we all know the story of salmon, our focal species tonight, who make that migration from the ocean to the natal streams to spawn and die and give their offspring the best chance of survival. So no matter the strategy, the eggs in the freshly hatched fish typically, or almost always, experience a higher mortality rate than the adults. If we think about that mola mola with her 300 million eggs, if 0.5% of those eggs made it to adulthood, that'd be 1.5 million adults from a single batch. I don't know how long it takes for mola mola to reach sexual maturity, 10 years, let's say. If that's the case, in 10 years' time, the ocean would probably be more mola than it would be water, right? If you had 1.5 million surviving every single year. So their strategy takes into account this ontogenescence and that early life mortality, where maybe 99.99999% of their eggs die, right? If a couple hundred of them make it to adulthood, that's a success for that mola mola. All right, we're going to narrow our scope down even more and look at just Chinook salmon. So Chinook are the largest of the Pacific salmon. They live anywhere from 2 to 7 years. And we all know that migration story of ocean to natal streams to spawn. Spawning occurs in Chinook salmon similar to many other salmonids. The female digs a red using her tail. She clears out a section of sediment that creates a divot in the substrate. That's called a pot or a pit. That moved material piles up downstream into what we call a tail or a tail spill. She'll deposit eggs at the bottom of that, and then move forward and recover those eggs with sediment. The male and the female will do this several times, and you'll end up with a little pocket of eggs buried underneath a pile of stones. And you'll actually end up with like a little lasagna down there where it's like sediment, eggs, kind of all buried in a neat little packet right at the bottom. And it's hard to see maybe. If we look on the diagram, we can see that the shape of the red actually helps direct flow from the river. These arrows are showing the way water is flowing through the red. The shape of the red actually helps direct flow into the sediment across those eggs, delivering oxygen-rich water for those developing embryos. And that female will lay anywhere between 3,500 and 6,000 eggs at a time. I have a little video here. So we can see the female right here in front in the foreground hanging over that pot or pit just underneath her. This is the male. He's going to come up and give her the sign that he's ready to spawn. All right, you see a cloud of milk coming out behind him. She's depositing eggs at the exact same time. Those eggs are landing at the bottom of that pit, and now she's going to move forward and bury those eggs like I talked about. At the same time that she's doing that, we can see drifting up over the top are actually some of her eggs that got kicked out of the red when she did that, and they end up traveling downstream. That's going to be important here in a minute. So, and then they'll repeat that process a couple times before they're all spawned out. Those eggs are nice and buried, and then they'll eventually go senescent. They'll die as close as they can to those reds. Yeah, yeah, one shot deal. Yeah. One shot. Yeah, they don't spawn again in their life. Yes.
Poor guys.
All right. I don't know. Okay, and we're back. All right, so there's that. Just watch that. Okay, now I'm going to introduce our fish counter. We're going to start with 5,000 eggs, freshly deposited and expertly covered by a slightly above average female Chinook. We're going to follow this clutch as they hatch and emerge from the gravel and make their way to the ocean, make their way through their migration to the ocean. I'm going to ignore any of the ocean portion of the salmon life cycle. I don't know where my cursor is. All right, yeah, for this presentation, we're going to ignore any of the adult section or the ocean part of the life cycle and focus just on from eggs to smolts, and smolts are the juveniles that are entering the ocean. I tried my best to pull mortality rates and survival rates from the literature when I could, so that we can whittle away our 5,000 number. A lot of these portions of the life cycle are very hard to monitor. These life stages are some of the least understood parts of the salmon life cycle. It's very difficult to count the number of eggs that are coming out of a female as she's laying them. It's even more difficult to track those eggs in the sediment and count how many are coming out. There are efforts to do that, both here in the Trinity Basin and abroad. So when I could, I pulled survival and mortality estimates from rivers and places that were as similar as I could to the Trinity to give us a little bit better of an idea of what might be happening around here. In no way are the numbers that we see today representative of what is actually happening in the river, right? This is more of an exercise to give us an idea of how these fish survive. So the life stages that we're actually going to look at are from egg to hatch, from hatch to emergence, emergence to fry, fry to par to smolt, and then ocean entry. And we're going to jump right into our first section. All right, these are eggs to alvin. While the eggs were the least mobile of the life stages that we're going to look at, that lack of mobility in no way lessens the amount of things that might kill them. From the moment they're deposited, there are factors that are beyond their control that determine their viability and ability to develop. First, they have to be fertilized. As we saw in the video, this happens external to the parents. There's a good chance when that female, not a good chance, but there is a chance when that female is releasing those eggs that they just fall outside of that cloud of milk. So the egg never meets sperm and that egg will never develop into an embryo. Even in that deposition and red building process, some of the eggs are lost. Like we saw in the video, some eggs are just kicked up over the top of the red to drift downstream and be gobbled up by any other critter that might be waiting downstream. All right, so even if they are fertilized, there's factors that affect the actual gametes, the egg and the sperm, that it will influence the ability for that embryo to develop. Looking at the two plots that I have up here, in the middle we have Johnson et al. That shows individual females, A through I, and the percent survival of their eggs, both in the river and in the hatchery. Now these females were paired with different individual males. And we can see that some pairings just had lower survival. All right, this is some parental effect that is, we're not really sure what it is. This publication didn't have a good, didn't go into any of the genetics as to why this might be happening. And then on the far left over here, we have Thorne and Morby et al. And this is just showing increased egg survival with increased egg size. Right? The larger the eggs that the female is laying, the better chance they have of surviving. An interesting note here is that when we have hatcheries, hatcheries tend to select for females that lay smaller eggs. So if you mix hatchery with hatchery fish consistently, you'll end up driving the size of eggs down. And with that, you'll end up driving survival of those eggs down as well, which may not be a big issue if those fish are only being raised in the hatchery, but if they start mixing with the wild population, you can see depressed survival from the reds in wild reds or natural reds. Okay, moving on to some abiotic factors, so things outside of the salmon itself that might affect their ability to survive. These two plots here are showing up here in the top right, incubation temperature and mortality. And on the bottom here, the percent of sediment that is less than 6.4 millimeters and egg to fry survival.
Question,
Yes,
what's the best temperature for the eggs?
10 degrees C.
One more?
10 degrees Celsius?
Thank you.
Yes.
Do you know that translation to Fahrenheit?
50 degrees Fahrenheit, yes. Oh yeah, so looking at the two figures, we can see that there's a sweet spot for survival right around 10 degrees Celsius. Sorry, maybe skip. Okay, so temperature and dissolved oxygen are two of the most important factors that have had a lot of attention poured on them because they affect egg development the most when they're in the reds. There's a sweet spot for development right around 10 degrees Celsius. We can see that mortality increases asymptotically, right? It increases quite quickly, right around 0 degrees or freezing, and right around 20 degrees Celsius, which is 68 degrees Fahrenheit. We get either too hot, too cold, and those eggs aren't going to make it. Now, oxygen, or dissolved oxygen in the water, DO, is related to temperature. The lower the temperature, the higher the dissolved oxygen. The higher the temperature, the lower the dissolved oxygen that's available to those eggs. So as long as the temperature stays in that safe range, dissolved oxygen should stay in the safe range as well. But flow and sediment can play an important part here. Remember that figure of the red, where the shape of the red actually helps drive oxygenated water down into the egg pocket. If the spaces between those rocks end up filled with small or fine sediment, we can decrease the amount of oxygen that's being delivered to those eggs, and we'll end up with a bunch of dead eggs, right? And that's what we see in the plot here on the bottom. As that percent of sediment less than 6.4 millimeters increases, all four of the data sets here saw a decrease in survival. A couple pictures from, well, two of them from recent work that I've been conducting on the Trinity Reservation, or sorry, the Hoopa Reservation, not on the Trinity River. These are done in a creek on the reservation. In my hand on this slide are 3 eggs that are at the eyed stage. So they developed up until they had an eye. You can see the embryo in there, but they stopped developing at that point, right? They died. We can see from that same batch, this bucket of fish that were grown in the hatchery, and they hatched just fine. So what happened here with these 3 eggs is we had placed them in a basket and placed them in an artificial red. So a red I dug with a shovel and a rake. And when I buried them originally, they were about 8 to 10 centimeters under the sediment. When I went to pull them out of the river to see how many had hatched, they were actually like 1.5 feet under some pretty fine sediment that had washed down from a big winter storm. So these fish were developing just fine, right? They made it to the eyed stage. They were a ways into development before that storm happened. It sealed them off from the oxygenated water, and they ended up not developing past that.
How did you find them?
We used a little basket, and the basket had a string coming off of it, and so it was hard, and we didn't find all of them because in addition to being buried, you also get some that were washed away, right? So some of them had more sediment pile up, others had sediment washed out, and we found them downstream, like jammed under a rock and also not alive. This other picture here, which a little bit of an older picture that you can tell by the color, is probably done in the 70s or so. I just thought it was neat. It shows some brother and sister Alvin that have hatched right next to some eggs from the same batch that never developed, right? Those were dead eggs to start. And that was likely something in that parental effect from the last slide, where for some reason something stopped the development of those eggs, whether they weren't fertilized or there's something genetic that just stopped them from developing. Meanwhile, their neighboring eggs made it through just fine. Okay, we're gonna go back to our eggs now, our 5,000 eggs in that expertly dug red. We're gonna say that fine sediment wasn't an issue. It was a normal amount, nothing excess. The genetics were didn't play a big part, and the river conditions were acceptable. They weren't ideal, but they were okay. How many fish do we think made it from our 5,000? Any guesses? Give me your percentage. 10%, 20%, half? 2,000. We're down to 2,442 fish. So we lost just over half, right? We lost 2,558 individuals. So our mortality ended up being 51%. Again, that was in a decent red, right? That was without anything major that could affect survival. So these fish will now be making their way out of the gravel. They'll start to swim up off the substrate, and they'll transition to feeding or exogenous nutrition. Maybe. All right, so our survivors have absorbed nearly all of their yolk sac. They're starting to swim up as fry. Fry are typically 30 to 40 millimeters. On the Trinity, maybe they're a little bit smaller, 25 to 30 millimeters. They feed on plankton, larger invertebrates, and any kind of suspended organic material that might come floating by. As they feed and grow, they transition to par, which is like our next life stage. Like we see this guy near the sediment here on the bottom. Par will narrow in their feeding on drifting terrestrial and aquatic macroinvertebrates, or any kind of bug basically that floats by them. Although they do find plant material in diet studies, and that's likely from just inquisitive feeding on anything that's floating by. They'll reach up and grab. So during these life stages, the juveniles will often form schools, and they'll use cover as often as they can. Cover can be larger substrate, like we saw that guy on the last slide sitting down by larger cobble, or an undercut bank, or a large woody structure. Now, why might we need to use cover and form a school? A large portion of mortality at this life stage comes from predation. Right? From the moment our babies are leaving the relative safety of the gravel, there are numerous predators out there that are dying to make an attempt to eat them if they stray a little too far from cover or a little too far from the school. Some natural predators they might run into, especially in the creeks, would be a rainbow trout or a steelhead like this guy up here. Any of the couple species of sculpin that we have swimming around in our local streams and river. There's also lamprey, which don't necessarily kill their host, but when you leave a wound that big on a juvenile Chinook, it's likely not going to make it, and the secondary infection will likely get a hold of it. There's also invasive species like this brown trout that was caught in the Trinity during Justin Alvarez's thesis work, if you're familiar with that. It had a belly full of, these are probably coho, but it had a belly full of salmonids. And then this catfish that was caught in the rotary screw trap just down near Helena, which likely washed over from the reservoir. So in addition to those, all these that you see here, there's also sunfish and crayfish that can easily grab any of our fish as they're starting to make their way out of the substrate. And then in addition to these aquatic predators, there's also death from above, right? They might be a little bit small still for the osprey, but the kingfisher and the heron down here and the egret and the cormorant and the merganser and the otter would none of these would hesitate to make a snack out of our fish at this size. All right, moving on to look at some of the abiotic factors. Wow, that plot doesn't look right. It's missing some stuff. This plot is looking at survival in the Sacramento River. On the bottom here is flow in CFS. This is a smaller creek, a tributary to the Sacramento, Mill Creek, also in CFS. And this is looking at temperature. On the y-axis for all four of them is survival. So flow and temperature are two important factors at this stage. There's also entrapment and stranding. Entrapment occurs when alevin are making their way out of that gravel. So after they've absorbed their yolk sac, they need to get up and start feeding. If any of that gravel is shifted around or again shrunk in size, right? Any of that small gravel moves in, it can not only cut off the oxygen, but it can stop the individuals from swimming up and out of the red pocket. So if they can't swim up and start feeding in time, they're not going to make it. Stranding occurs when spring flows or high flows come up, fish move into side channels, freshly open habitat to feed and take advantage of it. When those flows start to recede, if those fish don't take that cue to move out of those side channels, they can end up stuck in ponds or pools in those side channels, remain disconnected from the main channel. That leaves them open to easy access for predators, raccoons, or any of the birds that we saw. And those pools and ponds start to heat up really quick, DO will drop, and the water will disappear. So those fish won't make it either. So for temperature, ideally the water would remain in like in the 15 to 16 degree range. As it increases towards 20 degrees, we start to see survival decline. When it increases to those higher temperatures, fish will move towards cool water refugia, usually at the mouths of creeks, and they'll kind of crowd in that cold water to find a nice spot to hide from that warm main channel water. But when you get all those fish crowded into a small area, you just make them more open to predators, right? In addition, it's easier to transmit diseases when you get fish packed into a small space, and a warm river doesn't help with disease transmission as well. River flow can be a big factor in survival at this age. As we can see in these plots, as flow increases, survival increases. One main reason for that is the higher the flow, the less time they spend in the river. The faster we can get them out and healthy on their way out, the less chance they have of dying in the river. So we just see survival is higher.
About what month is this?
I'm not sure. I'm sorry.
I appreciate you saying that.
Yeah.
Does that not necessarily mean the survival rate overall is higher? It just means in the rivers.
Exactly. So each day that they're in the river, there's a chance of them dying every day they're here, right? If you get them out of the river faster, there's a less chance that they actually died in the river. Does that mean that they're in the best condition when they hit the ocean? Maybe not, right? If we turn the spigot up and we rush them out before they get a chance to feed and grow and are prepared to enter the ocean, maybe they don't make it when they get out there, or they're a little less likely to survive. Either way, the in-river survival could be higher if the flow is higher. All right, back to our fish counter. So we had 2,442 fish make their way out of the gravel, swim up and start feeding. They ran into their first predators, they had their first meal, and they had to find refuge from high flows and from those predators. Moving on to the next stage, we lost a total of 757 fish. That's not bad. We're down to 1,685. So that was a loss of just over 30%, and we had a survival of around 70%, or 69 and some change. All right, going into our last stage before we hit the ocean, from par to smolt. Survival from par to smolt has many of the same dangers that we saw in the last few life stages, along with a few new ones. Temperature and flow can still play an important part here. Higher temperatures and lower flow can lead to increased risk of mortality, similar to the last stage. But there's also a new stressor that they need to worry about, and that's smoltification. That's the process of a physiological process that changes our fish from these par to these smolt. Their gills and kidneys will be modified to better osmoregulate, so take care of the salt in their body as they transition from fresh water to salt water. Their color and shape will change, as we can see. They'll elongate, get bigger, and their metabolic rate will increase dramatically. These changes are stressful and they require an increased amount of energy. Increased energy means more feeding, or increased energy needs means more feeding, which means more risk taking. You end up running into more predators and opening themselves up to mortality. As they move downstream into the estuary, they end up running into new predators. So we may not have these American pelicans here, but that one does have salmon in its mouth, so I thought it was neat to include. We might have brown pelicans down in the Klamath River estuary. Birds of prey, larger birds, are likely keying into smolts. The marine mammals now become an issue. Seals and sea lions that can make their way up pretty far. And then, of course, the introduced species like striped bass, which love to put a hurt on juvenile salmon. An additional factor that plays an important role here in the Trinity River, ignore that picture for now, it's supposed to be a video, but it didn't work. We can watch it in a minute if you'd like. So an additional factor that plays an important role here at the Trinity is carrying capacity. In particular, the amount of space that's available for rearing juveniles at a particular stage or a particular river flow. As fry in our previous section, juvenile Chinook required shallow habitat with low velocity that's typically located near the stream margins. As they grow into par and smolt, they tend to move away from that slower water, move to faster water in deeper pools, deeper runs, and riffles. And that provides a better chance for feeding, right? More water passing by, carrying more food. So as our fish move downstream, they have to jockey for position with the other fish that are out migrating at the same time. River functions in the Trinity River have been heavily impacted by dam construction, and that led to a severe deficit of rearing habitat. Carrying capacity, as it declines, leaves fish competing for less optimal positions and pushing them into subpar conditions for feeding and rearing. The restoration sites that have occurred and that are continuing to occur in the Upper Trinity go through a selection process whereby we compare design alternatives and look at how those alternatives increase the carrying capacity for both fry and pre-smolt or smolts. This is from Upper Connor Creek, from the design selection process. That's the current construction that's happening just downstream from here. What are these, 950 CFS on the left side and 1,500 CFS on the right side. If we really got into it and looked closely at the colors here, we would see an increase in carrying capacity from 950 to 1150 CFS. That increase in carrying capacity just provides better opportunity for more fish. All right, now back to our fish counter. This is our last transition. As I said, this is a critical time for our school of juveniles, smoltification, larger predators, warming rivers, and fighting for that good habitat in crowded conditions. How many are left? So after this, they're going to be in the ocean. We had a total of 707 fish make it to the ocean, right? And I didn't plan that. 707 just came up naturally. I didn't try and, that's not my area code. So we lost about 58% of our fish from the last stage, around 978 individuals. So close to 1,000 fish died from par to smolt. So we had a fairly successful batch of fish that we followed. Not all reds are this successful. And a few of the studies that I referenced here had documented cases where reds had no surviving individuals, right? They never even made it to fry. They never emerged from those reds. When I was selecting the mortality and survival rates that I used to calculate these numbers, I tended to err on the higher side of their confidence intervals, using the means and the medians, and getting numbers like 20 fish making it out just seemed a little depressing, and I didn't want that to be the mood. So again, I kind of erred on the higher side of the survival mortality, but I still think it gave a pretty good, synopsis of what's actually happening out there.
Question.
Yes.
If we wanted to see a red in action, is there any place that you could direct us to that's reasonable?
Yes. Up at TR, like just below TRH, Sven Olbertson, one of the early restoration sites, there's like a fly fishing access area. If there's a path that goes down and you can go right to the water's edge. And last year there was a ton of fish spawning right at the side channel. Yeah. They'd be easy to see and you wouldn't even have to like get in the water.
Wonderful.
There's a deer back there. Okay, so this was a very introductory story that I told here. It doesn't convey the complexity of the relationship that Chinook and other salmonids have with the rivers that they call home. This picture that's here on the screen is part of the current survival study that Tiana introduced. We are 3 years into the study. There's 2 more left to go. This is data from the first 2 years. It's really hard to see on the screen, but there's actually 2 lines here, one line on top of the other. The colors represent the warmer colors, like the reds, represent higher mortality. The yellows would be areas of lower mortality or so higher survival. And again, it's difficult to see, but this area of red and this area of red are actually sitting on top of a yellow line. So an area of high survival that we saw in 2022 became an area of low survival. I'm saying that backwards.
What factors are causing that?
Exactly, right? And so we're in the middle of this study. It's pretty early on, and yeah, no, that's okay. Like, I gave a presentation on that and some conjecture about it during our science symposium. Temperature seemed to play a role, higher temperatures, and we saw increasing temperatures to a certain point. We saw increasing survival because the fish were able to grow faster. But after,
mortality
at the upper end, we started to see mortality drop down. So once we hit about 20 degrees C, we started to see that, yeah.
pretty low. Okay.
Yeah, well,
compared to
yeah, 68. What part of the Trinity is that? That's basically the whole reach from the dam to the mouth. Yeah, so this is really what this is telling us. The story is that survival and mortality can change from year to year depending on condition of the river, depending on condition of the fish. Without being able to gather that data for multiple years, if you looked at this for 1 year, you wouldn't have an accurate picture of what's happening in the river, right? Having a multi-year study that allows us to look at fish through a range of conditions will give us a better picture of what's actually happening and how mortality is being affected by river conditions.
I have a question.
Yes.
That 14% that made it to the ocean,
Yes.
is that sustainable to regenerate a whole nother year? And what is the tipping point towards not enough to keep it going? How close are we to 14%?
That 14%, like I said, is more of an exercise that I put together for this. The actual number is much harder to decode.
So how much need to get to the ocean in order for them to come back and try again next year?
Oof. Well, the ones that make it out this year aren't going to try next year. They're going to try in the next 2 to 7 years, right? Because they go to the ocean, they mature for a while before they come back. So the fish that are returning this year actually swam out anywhere from 2 to 7 years ago. So looking at the individual age classes, you want to know how many do we need in the ocean to come back in order to sustain the population is what you're asking. That's a really important question. It's also a really hard one to answer, right? There's a lot that goes into ocean survival that is out of our control, right? We need to have as many juveniles hitting the ocean as possible in the best condition to survive those ocean conditions to make it back, right? Yes. Yes.
You mentioned Connor Creek project. You did in the context
Mhm.
of was it artist mold? What age range is primarily looking for improved habitat in the area? Is that
In that area, I would say all ranges from fry, right? Because that same area, like you get reds up and down the river, right? From Hoopa all the way to the dam. So we'll have fry emerging at all throughout the river. So that fry capacity is important at Upper Connor Creek because we are going to have fish creating reds and laying eggs in that reach, in that restoration site. So you'll need that capacity for fry there. In addition, you'll have fish that are moving from upstream, from up here by the dam. They'll be passing through Upper Connor Creek on their way out. So having the increased capacity for par and smolt is also important because they will be traveling through there. And that's those kind of questions are going to be important when we wrap up the survival study because a large focus is what's happening in the restoration reach, in this upper reach. We have as many monitoring points here in the upper river, in the restoration reach, the first 40 miles, as we do in the bottom, like 2/3 of the river, right? I put out like 8 receivers up here by this dark red line, and I put out 8 receivers all the way down to the confluence. So we're really focusing in up here to see where that mortality is, see if and where that mortality is happening in the restoration reach. Anybody else?
Chad,
Yes.
can you describe the receivers and that mechanism?
Sure. Yeah, we can do that. Let me get through this, and then I'll definitely show you some of that stuff. So pick up where I was. All right. So unraveling that complex relationship, like we're talking about, is important for the interaction. It's important for those unraveling the complex relationships that dictate survival and mortality of Chinook is important to efforts to conserve this vital species, not just for the people that depend on it, but for the communities that depend on it as well, like us coming here to drink beer and sit around and talk about them. So our ability to improve survival rates of juvenile salmon is limited by the factors that we're able to actually influence. The data that we collect to inform our restoration and conservation efforts allow us to focus on factors that we can actually change and have a meaningful impact with, rather than spinning our wheels on things that are outside of our control or outside of our domain. For instance, if we know that eggs are not hatching due to fine sediment, we can utilize gravel augmentation to introduce the appropriately sized gravel to certain sections of the river to improve that egg hatching rate.
And for the lampreys.
And for the lamprey, sure. They need the appropriately sized stuff. I would have talked about lampreys tonight too. We could have done that. All right, so here on the Trinity River, the TRRP and its participating entities, Hoopa Valley Tribe and Yurok Tribe, and all of the federal partners and our state partners, have been fundamental in working to improve the habitat and the survival of juvenile salmonids here in the Trinity. I'm grateful for the opportunity to be here and to have worked with these people for the past couple of years. I know a number of them are leaving or moving on or changing career paths. And I just want to wish them all the best of luck in the future. And I hope that they are still around to give guidance, because I'm new here. I've been here for 6 years. There are people that have been here for decades. And I think losing them is a big hit to just the knowledge base. So I hope that they're around and leave their phone numbers on the desk so we can call them and continue to bug them and get them to help us fight for this shared resource. With that, I want to say thank you for coming. Thank you to the Trinity County Resource Conservation District, TRRP, and yeah, all the authors I cited, which are there if you want to read them. And then family friend Jane Desert, who donated all these pictures from Alaska and Sacramento.
All right.
Oh.
All right, I wasn't ready, sorry. Thank you, Chad. That was amazing.
Oh, yeah, no problem.
Round of applause for Chad. Thank you, thank you.